So welcome. We have made it to week 10, and we're going to be talking about regression this week. In fact, we're going to be talking about one specific portion of regression, which is why we use simple linear regression, and that is for making predictions about the future. Now, it's said that making predictions is difficult business, especially when they involve the future. But that's exactly what we're going to try to do. Let me talk about how we do that typically. So if I want to predict what's going to happen in the future, especially about people, if I start with what I know about people or about a person, I can usually make some good predictions, because the best predictor of future behavior with other human beings is past behavior. If I know how people have behaved in the past, what is their typical way of behaving, what we might call reputation, then I can make some pretty good predictions about how that person is going to behave in the future. This means that even if their immediate behavior isn't matched up precisely with what I know about them, I probably ought to trust that track record instead of their immediate behavior. Or as Dave Barry said, if you're with someone who's nice to you, but mean to the waiter, you are with a mean person. The snake in the grass doesn't have to bite you to still be a snake. If you know that someone has mistreated and cheated and lied and stolen in the past, but they're being really nice to you, chances are they're setting you up for that same old behavior. Or if you are with someone in a romantic relationship and that other person was cheating on somebody else to get with you, well then don't be surprised if you get cheated on, because you're with a cheater. You see how that works? Okay, so the way that we predict with other people is we take what we know about them and the way they've behaved, and we apply that to the future. Let's then take this same example with variables. And what we can know about variables is the way that those variables are related. That was the whole point of that correlation discussion last time. When we know something about the way that variables are related, we can use that to make a prediction. So let's say that I am going to pick one individual at random. I'm going to pick a guy from the US population. And I want you to tell me, how tall do you think he is? You predict his height of this randomly chosen individual. So what will be your best predictor? What model would you use? What do you know about a male from the US population that will give you the best prediction?
Use the average height.
Yes, you would. Your best predictor is going to be the mean of the population. So if we do a little bit of research and we find that the average male American height is 177 centimeters or 69.7 inches, approximately 5 feet 10 inches tall, if I select one person at random from the population and say, how tall is he, knowing nothing else, your best guess is going to be 5 feet 10 inches, because that's the average. But now I'm going to add some additional information. I'm going to select a guy at random from the US population, but I'm also going to give you one more bit of information about him. He is a basketball player. What are you now going to do with your prediction? Are you going to guess that same 5'10"? You're probably going to guess taller than that. 6'2", 6'4", 6'8". If I tell you he's a professional basketball player, 6'8". Right? If I tell you he's a high school basketball player, I'll go 6'2". You're going to take what you know from this additional bit of information and apply it to the mean, and you're going to adjust your prediction. Or if I tell you that this randomly selected male from the US population is also a horse jockey, now what are you going to do with your prediction? You got 5'10" as your starting point. That's the average. I'm going to go lower, maybe 5'2", maybe 5 foot tall. Again, you take what you know, this additional bit of information, you apply it to the mean, in this case, and you adjust your guess. That's what regression is. If you know nothing else, your best prediction is going to be whatever the average of the y-axis is. But if I give you additional information, you'll be able to add that to what you already know, and you'll be able to make a better prediction. So linear regression is a way of predicting. We're predicting an unknown y-score based on x scores from a correlated variable. So just remember, x and y, those are just variables. Height and weight, 2 variables. I'm going to predict your weight based upon what I know about your height. Or maybe I want to know if you are likely to succeed in college. And so we take what we know about the past. We know that if you have been successful as a junior high school student, and you've been successful in high school, you've earned high grades, that your likelihood of getting good grades in college is much higher, so we could predict based upon that pattern. Or maybe what we do is we give you some kind of standardized test, like the SAT, and we use that to predict the likelihood of your success in college. Now remember, there's always variability, and it may be that, in fact, I'm thinking of a friend I knew who fit this pattern very well. He did pretty well. He was a decent student in high school, but he went to college, and he kind of flaked out, and he ended up, I don't know if he ended up dropping out, but I know his grades were really, really bad, especially that first semester in college. Now later on, he got his life together a little bit more, and he did better. But his prediction, if we were just looking at his high school test scores, his prediction would have over-predicted his actual performance. So there would have been some error in what we predicted and what we observed. Now another time when we want to predict the future, is we want to know if you are going to be successful in this job that you're applying for. I mean, you seem like a wonderful person, you're very friendly, you're outgoing, but do you really have what it takes to be successful? How could we know that? Well, maybe what we do is we've done a job survey in which we've selected the people who are the best performers at our organization. And we have measured some things about them in the way that they perform. We've measured some variables about them. And we've created a profile in which we can give you that same test, and we can predict based on really how closely you align on those same variables with what we know are already high performers. Even better, we wouldn't just use the high performers, we'd use high, medium, and low performers, because it's quite possible that the predictors that we choose aren't really great predictors after all. Just because a lot of people who are successful have this in common doesn't necessarily mean that's the causal factor. Although if we see them on a scale, high, medium, and low, and then we see a scale difference, that's probably going to be a better predictor. So for example, going back to SATs, SAT scores do predict grades in college, but they're also a really strong predictor of family income. People whose families have more money also tend to score more highly on the SATs. So simply having that one data point is going to give us limited information. Then the best way to predict college or job applicant success is probably not to rely upon just one, especially one standardized measure, but rather to use a whole battery of tests or measures. So not only do I want to see your SAT scores, but how did you do, what were your grades in school, and what activities did you participate in? And we can use all of that information to make a better prediction. Will it be perfect? Will it be foolproof? No. And that is also one way to make sure that we get people who are like the people we already have. So what we tend to do with that kind of predictive model is we just get more of the same. Now, if that's what you want, that's one outcome. But if we're interested in different outcomes within our organization, we want to consider the utility of those predictors. Last time I told you all about correlation, which I said was relationship, but it's relationship between variables. So we learned about R. Do you remember what R stands for? Regression. So that R value of the correlation is how we summarize the strength and the direction of the relationship between the variables. And this is going to come up in regression. We're going to actually calculate a correlational coefficient as we do a regression. And when we have a simple regression, we'll have one coefficient, and it will actually be the correlation. It'll be the R value, and we'll see that. When we have multiple correlations, then that changes the R value because we don't have just a correlation, we have a partial correlation. And that's what we'll talk about next time with multiple regression. But for now, we're going to build on what we already know. Correlation tells us that variables are related. If a correlation exists, well, then we can use regression to predict, based on that relationship, the Y value from the X value. This is called linearity. There's a linear relationship between the two. So obviously, the stronger the relationship between the variables, the better they will be as predictors. Last time we talked about the temperature and how much cold soda or hot chocolate we would sell. There's a pretty good prediction that when it's 40 degrees out at the football game, we're going to sell a lot more hot chocolate. And when it's 80 degrees, we're going to sell a lot less hot chocolate. So we can then predict how much hot chocolate we need to make for the game upcoming just by looking at the thermometer. It's going to be 85 degrees on Saturday. How much hot chocolate do we need? We're probably not going to make any. But if it's going to be 30 degrees, let's make some hot chocolate, get some extra marshmallows. Everybody's going to want something to warm up. The stronger the relationship between the temperature and the hot chocolate sales, the better prediction we can make. All of this collapses upon a straight line. So what we are doing is taking all of those dots that we've seen in our scatter plot, and we are making them fit a straight line. This is why it's called linear regression. And we're going to use this formula, this y equals a plus bx formula, to represent our straight line. In this example, I'm using age and height. So based upon your age, how tall will we predict that you are? And we see the age range runs from 4 years old to 12 years old. So this is a pretty good predictive model. If I ask you how old someone is who is 8 years old, if I ask you how tall someone is who is 8 years old, we can use this model and go over to 8 and then up. Well, which of those dots are we going to choose? And the answer is we're not going to choose any one particular dot. We're just going to go to that straight line that's running through the dots, and that's going to be our best estimate then for their height. That's how we're using this straight line. If we don't have any other information, we're going to predict with the mean. And what I want you to see is that predicting with the mean, there's always going to be some error. In this case, I'm using my pirate linear regression, and I want to predict the support among the crew for mutiny. If I know nothing else, what's my best prediction? It's whatever the y mean is. So I would just use that horizontal line. That's my starting point. What I want you to notice is to the right, there's a lot of plus signs. Those dots are above the line. To the left, there's more negative signs. Those dots are below the line. Those are the errors. So the dotted lines represent residual variance, what we call error. Error in prediction. But now, watch those pluses and minuses when I adjust the line based upon what we know about the correlation between cases of scurvy on board the ship and support for mutiny. What I want you to see is those errors are smaller. We have minimized the errors. So now we've taken a second variable, we've applied it to what we already knew about our first variable, and we've made a better prediction by minimizing the error. This gives us the ability to predict we're predicting a y value based upon a given x value, such as if I know your age, I can predict your height. And what I want you to see is this y, and then the other one has a caret over the top of it. That is called y hat. There are other ways of representing this. I'll show you an example of a y prime. All of them mean the same thing, which is that there is a predicted value. This is what I predict based upon a known x value. In our textbook, you are given this equation. So it's y hat equals b sub 0 plus b sub 1 times x. That is where we're going to land. So I've given you this as a starting point in case, as you've read in the textbook and you're trying to apply that with what I'm showing you now, you might say, well, I remember something like this, but I don't remember exactly what you're showing me. What I want to do is simplify all these b sub 0, b sub 1. I'm going to use a simpler formula. It's just the formula for a straight line. And it is the y hat equals a plus b times x. I'm going to simplify it. Once you get these ideas, then we'll actually substitute the correlational coefficients, or we'll substitute the coefficients for a and b. And ultimately, when we get to multiple regression, we'll have a b1 and a b2 and a b3. Let's simplify it for now, get the concept, and then we'll expand upon that. So what are the portions of this formula that we're dealing with? The y hat is a predicted value. Knowing your age, what do I predict is your height? Your predicted height is y hat. So predicted value based on that straight line. A is a constant. It's also called the y-intercept. So it's the value when x equals 0. So when your age equals 0, how tall do I predict that you will be? And already you see that this is going to have some limitations. There are some things, there are some variables for which there is no true 0 value for x. Let me give you an example where there is. So if I want to predict how many sandwiches, how many hamburgers you're going to buy, if I know that your bank account, or let's say your wallet, has a value of 0, in other words, you don't have any money, I can make a really good prediction about how many hamburgers you're going to buy. Because that's a true 0. You got no money, you're not buying any hamburgers. That I can figure out. But what if I'm using IQ as a predictor? Can IQ be truly 0? Or if I'm using height as a predictor, can height be truly 0? There's a lot of variables that there's no true 0. They still have this constant, this value that we assume if x equals 0, but it may not be in the real world. It's just mathematically how we're using this as our predictor. B is the slope of the line. That's really just how tilted that line is, how close it is to horizontal, or maybe a 45-degree line. That's B. It's the measure of that. And then x is a raw score. So if I know A and B, I could plug in an x value and predict y using that value of the straight line. But that's what we're going to ultimately lead to. So to reinforce this idea, the A is the y-intercept. This is also the one that we're going to call b sub 0. The value of y when x equals 0, it's a constant in the output. And we'll see that in the JASP examples that we're working with. The value for b is the slope, the steepness of the line. This tells us direction and rate of change. So just think of this slope as a slide at the playground. If we have a slide that's just very low, then you might still slide down it. Certainly if you took your ball, it will roll down that incline, but it'll roll at a slower pace than if we have a slide that's at a 45-degree angle, where you would slide much more quickly, or that ball would roll much more quickly. The steepness of that regression line tells us about the rate of change. small changes in x with a really steep line can result in large changes in y. But if we have a line that's just tilted slightly, it's fairly close to horizontal, it's going to require greater changes in x to see a change in y. So it's intuitive, and if you just think about a slide, direction and rate of change. This is the formula for a general equation, first of all for a straight line, and then the b sub 0, b sub 1 equation, that would be for a regression equation. So all I've done is just plugged in those coefficients. Now this is the general equation. It doesn't become a true regression equation until I plug in numbers. So once the values have been plugged in, the actual numbers from our regression model, when those are plugged in, now we have a regression equation. We have an equation that we can use. So if I give you an x value, you would plug it in, you would multiply it by 12.11, and then you would add 6.33, that would be your predicted value. So we are going to use x to predict y, more accurately, y hat. Since we're using x to predict y, x is going to be the predictor variable. And we are predicting a y value. Y would be our outcome variable. We could think of this, because we're using the general linear model, and ANOVA would be part of the same general linear model. We could think of the x, the predictor, as the independent variable, and the y as the dependent variable. Nothing wrong with that. That's what they are. That's exactly what they are. But when we use regression, we talk about them as predictors and outcomes. In this example, SAT is a predictor variable, college grades are the outcome variable. You will sometimes see the criterion variable used in place of the x, but if you see criterion, that's referring to an x variable as well. I think it's simpler and cleaner, which is the way that I prefer to teach. Predictor and outcome, that's what we're going to call it. Now, if you have a perfect correlation between two variables, prediction is really easy. I gave you the example of night and day. So I said, if it's 3 o'clock in the afternoon right now, what do you predict that it will be in 12 hours? 3 in the morning, it's going to be dark. There's this perfect correlation between night and day. Makes prediction really, really easy. But in the real world, those kinds of predictions aren't terribly useful. They're just far too simple. We want to predict something with a little more variability, because that's a much more useful predictive thing. Everybody can predict day and night, but it's the math that is required to predict a complex outcome based upon a number of predictors. So if we have perfect correlation, we can have a perfect prediction, but in the real world, we don't have that. What we do have are variables, numbers that vary, and we're going to use those to predict a certain amount of the variability within our model. This is the method of least squares. So you remember when I was showing you a straight line as a predictor, and then we tilted the line and the errors were minimized? What we are minimizing is the error in the sum of squares. So those pluses and minuses, those are sum of squares values. We are minimizing those. We want the line that gives us the least amount of error, hence the method of least squares. And that is something that you will see, and it will make sense as you use it. I just want you to know that terminology, because it does pop up in textbooks. There's actually other methods that we could use besides the least squares. This is the one that we use the most because it is the easiest to understand. In fact, even easier is if we use the example of pi. This pi represents all of the variability in our model. So when I talk about variance explained, how much of the variability is explained, the whole pi is the total variance in the data. The amount of pi that is left would be the variance I can explain with my model being a straight line. But there will always be the unexplained variance. Now this would be an excellent predictor because we see there's a very small amount of unexplained variance compared to the amount of explained variance. This, if we think just in terms of variability, would be an excellent predictive model. Not all models are this good. Or maybe we have multiple variables that we use as predictors that give us a much better prediction. So we could slice the pie. We could partial out the variability. How much does variable x explain? How much does variable x2 explain? How much variability does variable x3 explain? So slices of pie is actually a pretty decent analogy for understanding all of the variability in the model. How much does each variable explain? And then how much is left over? How much is left unexplained? We can make predictions based upon our data, but what will sometimes happen is people will want to predict outside the range of the data. Remember I said that predictions are difficult, especially when they involve the future. Sometimes people want to take what we know from a model and say, well, that means that we can extrapolate that to values that aren't truly represented. So what you should do, if you're going to use a model for prediction, is know the range of the x variable, know the range of the predictors. So in this case, I have age and height, where the age runs from 4 to 12. So here we're predicting heights for children. If I ask you, how tall will you be based upon this model when you're 40 years old? We could still use the regression equation that created this straight line, but here's what it would look like. At age 40, we predict you'll be 12 feet, 8 inches tall. Obviously, that's not going to happen. Another example, if in February I say to you, we have had so much snow this winter, if it keeps snowing like this, we're going to have 12 feet of snow by the 4th of July. That's pointless because I'm predicting outside of the range. Snow is in the wintertime. Right? When it becomes summertime, everything changes. These values that work for age and height for children don't work for adults. So we want to be cautious about predicting outside of the range. Outside of the range being the range of our x values predictors. So in this case, 4 to 12, the line works really well. Maybe age 13, maybe. But certainly not age 20 or beyond. This line is going to break down very, very quickly in its predictive ability. It's called prediction outside of the range. The predictor that we're going to use is the r squared. In the lower right, you see the sum of squares for the model over the sum of squares total. Basically, if you have a pie plate full of pie, we've got a good predictive model. What we do is we take the r value for any predictor and we square it, and that explains the variability. So if our r value is 0.50, we square that. 0.250 is the r squared. And then turn that into a percentage. So move the decimal 2 to the right. 0.25 becomes 25%. Therefore, if two variables are correlated at a 0.50, the x value is explaining 25% of the variability of the y variable, which would be actually a pretty darn good predictor. This is also called, or is the same as, the coefficient of determination, the r squared. So we'll be able to use this example, we'll be able to use the r squared as we make some predictions. It will become much more useful as we go into multiple regression. Now that we know a little bit about prediction, our next step will be to go into how we actually create a regression model. That's what we're going to talk about next time. And then, following that, I'll be talking a little bit more about the multiple regression steps, which is applying what we know in a little bit broader way. So, before we wrap up, do you have any questions about what we talked about as far as predicting the future? Thank you so much for being here, and I'll see you guys next time.